Hello students, today we are going to learn the shape of liquid drops on a solid surface. Now suppose theta is the angle of contact between angle of contact of that liquid. Let T1 be the force due to surface tension at liquid solid interface. T2 be the force due to surface tension at air solid interface, and T3 the force due to surface tension at air liquid interface. So in this diagram you can see that this is solid and you have a liquid drop here, and here it is air, and depending on that we have marked the force T1, T2 and T3. So this is T1, this is T2 and this is T3, that is air solid air liquid interface. Now from this diagram you can say that if you take a component of T3 on this side, it will be T3 cos of theta. So from the diagram we can say that T2 is equal to T1 plus T3 cos of theta, like this. And from that you can write cos theta is equal to T2 minus T1 upon T3. Now depending on which force is more or which force is less, we can find out whether the theta is acute or obtuse. So if in case 1, if T2 is greater than T1, then from the equation we can say that T2 minus T1 is obviously less than T3. And in such case cos theta will be positive. From this formula we can say, and theta will be acute. So in this diagram you can see that the angle of contact theta is acute. So if T2 is greater than T1, then theta will be acute and you will get this kind of liquid drop. Then you have case 2, that is T2 is less than T1. So if T2 is less than T1, then T1 minus T2 will be less than T3 and cos theta will be negative. In such case your theta will be obtuse, that is greater than 90 degree. So in this diagram you can see that your theta, that is angle of contact, is obtuse and you will get this kind of shape of liquid drop. Then you have case 3. So if T2 minus T1 is equal to T3, in such case your cos theta will be equal to 1 and theta will be nearly equal to 0. So in such case your angle of contact will be 0. Then the fourth case is if T2 minus T1 is greater than T3, in such cases T2 will be greater than T1 plus T3 and cos theta will be greater than 1, which is actually impossible because the largest value of cos of theta is 1. So in such cases the liquid spreads over the solid surface and the liquid drop is not formed. So this is about the shape of liquid drop on a solid surface. Now there is another thing, another topic is that pressure on the surface of the liquid. Pressure on the surface of the liquid, we can just make it more simpler by saying if there is a surface of the liquid, then pressure, comparing the pressure between the surface above the liquid and below the liquid. So if you consider a plain liquid surface as shown in this diagram, so we will consider the resultant force due to surface tension as Ft, and here it is A point and here it is B point at which one molecule is there. So at resultant force due to surface tension, in such case plain liquid surface will be 0 and this Fa is the resultant force due to the atmospheric pressure. So in this case Ft is equal to 0, so only Fa decides the pressure and pressure at both the points Fa and Fb will be same. Now if your liquid surface is convex liquid surface, as you can see in this diagram, if the liquid surface is convex, then you can say that the resultant force due to surface tension Ft on the molecule B is vertically downwards towards here, and the force due to the atmospheric pressure is also downwards. So this force adds up to Ft. So Ft and Fa, they both act downwards, and because of that there is pressure at point B is more as compared to pressure at point A. So you can say that the pressure on the concave side, so this inner side that is inside the liquid, pressure on concave side is greater than the pressure on convex side. Okay, so in this case pressure here is more as compared to here. Then the third is a concave liquid surface. So in case of a concave liquid surface, the upper surface will be concave, and if you consider from inner side, then it will be convex. So in such cases, the force due to surface tension will be vertically upwards and the force due to atmospheric pressure is as usual downwards. So these two are in opposite direction. Now as these two are in opposite direction, the net downward force which is responsible for the pressure at B is less than Fa, because obviously these are in opposite directions, so some part of it is cancelled out. So we can say that the net downward force responsible for the pressure at B is less than Fa. So in such case, you can say that the pressure on the concave side, here outside the liquid, is more than the pressure on the convex side, that is inside the liquid. So here pressure is more and here pressure is less. So this small example gives you the variation in the pressure depending on what kind of liquid surface you have. So this is all for today's lecture. Thank you so much.